Good morning, all. I'm Gomati, Assistant Professor from the Department of EEE, St. Joseph College of Engineering. My field of expertise is power electronics and drives. And in today's lecture, I'm going to discuss about the design of modulus counter. Okay. So what is a counter first? It is used for counting the states. And modulus counter, it is a type of synchronous counter. There are two types of counters like synchronous and another one is asynchronous, right, counter. In synchronous counter, we are going to give clock pulse to all the flip-flops simultaneously, whereas in asynchronous counter, the output of one flip-flop is going to act as the clock pulse for the next. That means we are not going to provide clock pulse simultaneously to all the flip-flops. So you all know flip-flop is the basic memory unit which can store 1-bit information, right? And the basic building block for any counter is a flip-flop, right? So modulus counter, it is also a type of synchronous counter, okay? So mod 5 counter, in this lecture I am going to design a mod 5 counter by using a T flip-flop, okay? So mod 5 counter, any modulus counter, it is going to count n state. Here, since it is a mod 5 counter, it is going to count five states, right? The first step in the design of counter is draw state diagram. First, let's see what are all the different states available. For an instance, it is going to mod 5 counter is going to count first 0, then 1, then 2, then 3, then 4. It counts from 0 to 4. So assign this as state A, this is state B, this is C, this is D, and this is E. Okay. So state A is 0, 0, 0, B is 0, 0, 1, C 0, 1, 0, and I have assigned state D as 0, 1, 1, and E is 1, 0, 0. So now we shall draw the state diagram for this. So the first state is A. Okay, next to this state A, it goes to state B, then state C, then D, then state E, then again it will return back to state A. Okay, after E, it will again return back to A. Okay, so this is the state diagram. Okay, we have completed the step 1. Next to this, draw the state table. State table, it has present state, and next state information. For example, my first state is A. After state A, the next state will be B, right? So I've written all the 5 states, that is A, B, C, D, E. So after state A, it goes to state B, right? Now the present state is B. What is the next state? It is C. So after B, it is going to the next state C. Again, now the present state is C. After C, what is the next state? It is D. Now it is here. The present state is D. Next to this, the next state is E. So when the present state is E, the next state is A. From the state diagram, we can write that. This is step 2, right? Next, step 3. Okay. In step 3, we need to assign binary values for the state, and we need to plot the transition table by using the excitation table of T flip-flop. Okay. We need to plot transition table. So in the transition table, we have present state, right? In the present state, here we have 3 bits, right? So I've taken it as A, B, C. Then the next state, this is A plus. That is next state I have given A plus, B plus and C plus, right? And here I am going to use the T flip-flop, right? Since here for the state A I have assigned 3 bits, for each bit I need to have a flip-flop, right? So I am naming the flip-flop as TA, TB and TC, right? This is present state, this is next state, and here I need to write the flip-flop inputs. For this, I need to know about from the present state and next state value, I need to judge what should be the input value given to the flip-flop. That I need to take it from the excitation table. Excitation table of T flip-flop. So excitation table of T flip-flop, that is Q is the present state, Q plus is the next state. With these two information, I can write what should be my T input. So the possible combination is like 0, 0, 0, 1, 1, 0 and 1, 1. Here when the present state and next state value is 0, then the T input should be 0. When the present state is 0 and the next state is 1, in that case, T input should be 1. Similarly, when my present state is 1 and the next state is 0, here my input should be 1. Again, when the present state and next state value both are 1 means the input that should be given to the T should be 0. This is the excitation table of T flip-flop. By using this table only, we are going to fill the values in this TA, TB and TC column, right? So here, let us write the state. The present state, that is, this is present state and this is next state. So the first state A, what is the binary value assigned for state A? It is 0, 0, 0. So I am going to write 0, 0, 0, right? The value assigned for A is 0, 0, 0. So what is the next state for this present state A? The next state value is B. What is the binary value assigned for the state B? It is 0, 0, 1. So I am going to write the next state value as 0, 0, 1. I am going to rewrite these two columns by assigning value for this binary value for the state A, B, C, D, E. That's it, okay? And here, the next thing is B here. B, for B, the value is 0, 0, 1. And for C, here you can refer here, for C, the value is 0, 1, 0. 0, 1, 0. Then C, for C, the value is 0, 1, 0. For D, the value is 0, 1, 1. And lastly, the last state, that is E, the value assigned here is 1, 0, 0. Here for C state, the next state is D. The value assigned for D is 0, 1, 1. And for the state D, that is 0, 1, 1 is the state D. For D state, the next state value is E. Here you can see the next state E is assigned a binary value of 1, 0, 0. Then after the state E, it is returning back to A. That is, the binary value assigned for A is 0, 0, 0. So I have just written this table by assigning value for the state. I have written the binary value which I have assigned for state A, B, C, D. I have simply written the binary value in the present state and next state, right? Now by using the excitation table of this T flip-flop, I am going to fill the input for the T flip-flop here. For TA, I am going to compare these two values, A and A plus value. A is present state value and A plus is next state value, okay. So here the present state value is 0. Here in this A plus column also you can see the present state value is 0. The value is 0. So the present state and next state value is 0 here. In this first row, if you compare this, here the present state value is 0. Here also the present state value is the value of A plus, that is the next state is also 0. So when both the present state and next state values are 0, from the excitation table of T flip-flop, what should be the input given? It should be 0. From this, the input given is 0. Now, check the second row. Here also, the value is 0. In the A plus column also, the value is 0. The present state value and next state value is 0 here. Again, from this, I can write if the present state and next state value of 0, the T input should be 0. If you take row 3, here also, the present state and next state values are 0. So, I am writing 0 here. So, in the fourth, here you can see the present state value is 0, but the next state value is 1 here. So, if the present state is 0 and the next state value is 1, what is the T input given? It is 1. The last row, the present state value is 1. Here, next state value is 0. So, the present state is 1, next state is 0 means what is the T value? It is 1. Right? Similarly, compare B and B plus. Okay. Here you can see the B value is 0, B plus value is 0. If both are 0, then T input is 0. Okay. Here again, B value is 0, B plus value is 1. For 0, 1 from this excitation table, I can write the input is 1. Then the third row, B value is 1, B plus value is 1. When both the values are 1, from here I can conclude the T input should be 0. And if you take the fourth value in the B column, that is here it is 1, B value is 1, and in B plus it is 0. So, for 1, 0, the value is 1. Then here 0, B value is 0, B plus value is again 0. Both are 0 means from the excitation table I can write for 0, 0, T value is 0. Similar to this, you need to compare C and C plus. Here 0, 1. So, here the value is 1. Again here C value is 1, C plus value is 0. So, here the value is 1. Here the value is 0 and the C plus value is 1. So, again 1. Here the value is 1, C plus value is 0, again 1. Here both the values of C and C plus are 0. So, here it is 0, right. So, now I have completed the transition table for designing the counter. Okay. After this, the step 4 is to derive the input equation of the flip-flop by using K-map. Okay. Step 4, derive input equation of flip-flop by using K-map. Right. So, here I need to derive 3 equations, one for TA, TB and TC, right. So, let me draw the K-map for finding out the value of TA. Okay. Here you have 3 variables, that is A, B, C. So, we need to draw a 8 cell K-map. So, this is a 8 cell K-map. Here I am assigning the value A bar, A, here it is B bar, C bar, B bar, C, B, C, B, C bar. You all know in K map, we are going to follow the gray code. So here it is 0, 1, here it is 2, then here it is 3, right? Now I am going to fill the values for this TA, okay, for this column. I am going to fill these values, right? For 0, 0, 0, TA value is 0. So here it is 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. So for 0, 0, 0, I am assigning the value here, the first for 0, 0, 0 value. What is the value of TA here? It is 0. Similarly, for 1, 0, 0, 1, the value is 0. Next is 0, 1, 0, that is the value is 0. 0, 1, 1, the fourth column, the value is 1, right? Then 1, 0, 0, the value is state, don't care. Next, plot K map for TC. This is A bar, A, B bar, C bar, B bar, C, B, C, B, C bar. I am going to fill the loss column, that is TC column. Here 0, 0, 0 is 1, 0, 1, 0 is 1, 0, 1, 1 is also 1, and 1, 0, 0, the value is 0. The others are don't care, okay. Now we need to group the adjacent ones. We need to do K-map simplification. Here you can see the K-map simplification. We can group these two, and the value of this grouping is BC, right? For this column BC, the row we have A and A bar, so it will cancel out. Plus the next grouping which can be done is this quad grouping, right? For this the value is A. So the equation for TA is BC plus A, okay. Next, K-map for TB. Here there is one quad group possible. Here the common term in these two columns is C, right? So the value of TB is equal to C, right? And next here also one quad group is possible, and for the value of TC is A bar, right? So now we have derived the input equation of the T flip-flop. TA is BC plus A, TB is C, and TC is A bar, right? And the final step is to draw the diagram, okay, logic diagram. So here we have 3 flip-flops, TA, TB, and TC. So we can put 3 flip-flop blocks, that is, this is TA, this is TB, and this is TC. As I said, modulus counter is a type of synchronous counter. We are going to give clock pulse simultaneously for all the 3 flip-flop, and this is the clock input, okay. And for TA, here you have QA, QA bar, here QB, QB bar, here you have QC, QC bar, right. For TA, the input needed is A, B, C, okay. So here we can draw the 3 inputs. This is A, B, C. And for TA, we need B, C plus A, okay. So here we have BC, okay, we are including an AND gate, and here we are giving the A input to the OR gate. So here you get A plus BC, and this is given for this flip-flop TA, right? And for TB, what is the equation we got? C, right? So directly from here, I am going to take C value, right? Then for TC, we require A bar. So from A, here I am going to use one NOT gate, right? Which will be given here, okay? So this is the logic diagram of mod 5 counter using T flip-flop. So this is how you need to design a modulus counter, right? Hope you all understand. Thanks for listening.